Have you ever had a moment where you realized things weren't as they seemed? Perhaps a magic trick fooled you, or you saw an optical illusion and questioned your eyes. What if everything is like that? What if reality itself is not as straightforward as you believe? In this exploration, we're going to uncover some astonishing truths that will challenge your most basic assumptions about the world. Get ready, because by the end, you might feel like you've taken the red pill and seen the Matrix for what it is. Take a moment to look around you. The room you're in, the device in your hands, your own body, it all feels so real, solid, and obvious. You've navigated reality your whole life, trusting your senses and common sense. We humans tend to believe that the world is exactly as we perceive it, that our everyday experience is the full truth. This is the common belief many of us live by. Seeing is believing. But what if I told you that reality is not quite what you think it is? In fact, it's far stranger and more fascinating than our intuitions let on. Throughout history, each time we've peeled back a layer of nature, we've found that reality is far richer and stranger than our intuition. Ancient peoples didn't realize Earth was a sphere orbiting the sun. They didn't suspect invisible forces like gravity, germs, or magnetism. In the past few centuries, science has steadily revealed a hidden world beyond our senses and expectations. Now we know that what you see is not necessarily what is actually there. Our everyday experience is just a thin slice of an immense, bizarre reality. Contrary to the comfortable illusion we live in, the solid world around us is mostly empty space. Time can stretch and bend. Fundamental particles behave like mystical probabilities. And there's even a serious scientific argument that our entire universe might be a sophisticated simulation. This isn't science fiction. These are real theories and discoveries backed by evidence. It's enough to make anyone question everything. But don't panic. Instead, get excited, because understanding these mind-bending truths will give you a whole new appreciation for how amazing reality really is. In this journey, we're going to pull back the curtain on reality. We'll start with the things you take for granted, your own senses, and show how they only reveal a tiny slice of what's out there, and sometimes outright deceive you. Then we'll dive deeper into the illusion of solidity. How the matter that feels so firm is mostly nothing at all. The flexibility of time and space. Time isn't as constant as your clock suggests, and space can warp. And the bizarre rules of the quantum world, where particles play by completely different rules than big objects. We'll even entertain the provocative idea that the entire universe might be one big simulation created by an advanced intelligence. By the end of this epic exploration, you might feel like Neo from the Matrix, waking up to a new world. Except this isn't a movie plot. This is our actual universe, as revealed by modern science. Ready to have your mind blown, in a good way? Let's jump in. As Morpheus said in The Matrix, if real is what you can feel, smell, taste, and see, then real is simply electrical. Signals interpreted by your brain. In other words, things are not always what they seem. Brace yourself. The true nature of reality is about to defy everything you thought you knew. And it's more fascinating than any fiction. On to the first revelation. Imagine being almost completely blind without realizing it. In a way, you are, at least when it comes to light. The human eye perceives only a tiny sliver of the electromagnetic spectrum. In fact, all the colors we see make up about 0.035% of the full spectrum of light. That means 99.9965% of all light, from infrared to ultraviolet, X-rays to radio waves, is totally invisible to us. You might think you see the whole world around you, but you're actually missing virtually all of the light show happening in the universe. Our eyes are basically keyholes, letting in only a narrow beam of reality. What we call visible light is a tiny rainbow within a vast ocean of electromagnetic radiation. To appreciate what we're blind to, consider the kinds of light we can't see. Infrared radiation, light with wavelengths just longer than red, is all around us, emitted by warm objects, including you. Ultraviolet light, beyond violet, is abundant in sunlight. Our eyes pick up none of these, but plenty of other creatures. Eyes do. Bees, for example, can't see red, but they can see ultraviolet. This reveals brilliant patterns on flowers that are invisible to us, like secret neon guide marks pointing to the nectar. What looks like a plain yellow flower to you might have a flashy bullseye in UV that screams, "Drink here," to a bee, and it's not just bees. Snakes like pit vipers sense infrared radiation, essentially body heat, allowing them to see warm-blooded prey in complete darkness. Birds, unlike us trichromatic, three-color, the humans, typically have 4 types of color receptors, tetrachromatic vision. Many birds can see into the ultraviolet range. For instance, kestrels, a kind of falcon, track mice by following the UV glow of rodent-urine trails, a visual superpower totally beyond human experience. Some flowers and bird plumage have ultraviolet patterns for mating displays, visible to birds but invisible to us. And then there's the animal kingdom's color champion, the mantis shrimp, which has over a dozen types of color receptors compared to our 3. The world might look unbelievably rich, or at least very different, to a mantis shrimp. Though, ironically, their brains handle color in a way that might make them less discerning than we'd think. Our other senses are similarly limited. Dogs experience a world of smell far beyond ours. A dog can detect layers of scents and faint odors we'd never notice, effectively seeing a whole landscape of information via smell. Elephants and whales communicate with infrasound, sound, below our hearing range, that can travel for miles. These rumbling calls are so low-pitched we don't even know they're there, but elephants can hear and even feel them. At the other extreme, bats and dolphins use ultrasonic clicks above our hearing range to echolocate, painting detailed mental pictures of their surroundings in complete darkness using sound. We are utterly deaf to those frequencies. Some sharks and rays can detect electric fields given off by other animals, and migratory birds navigate by sensing Earth's magnetic field, abilities completely outside our sensory toolkit. In short, many animals are sensing aspects of reality that we simply cannot. Fortunately, humans have found ways to extend our perception using technology. We've built instruments that detect forms of energy our senses can't. Radio telescopes see radio waves from galaxies and nebulae, translating them into images. Infrared cameras can show us heat patterns in complete darkness. We use X-rays to peer through flesh to see bones, and ultraviolet sensors to observe high-energy processes in space. We've even detected gravitational waves, faint ripples in space-time, from colliding black holes using giant laser interferometers, something no biological sense could ever feel. Each of these tools gives us a new window on reality, revealing phenomena our eyes, ears, and nose alone would never notice. Through science, we've managed to glimpse a bit more of that unseen 99.9965% of the electromagnetic spectrum and other elusive signals, bringing more of reality into view. Even within the narrow band we do perceive, our senses can be deeply misleading. Your eyes, for example, have a literal blind spot, a place on each retina with no photoreceptor cells where the optic nerve exits the eye. You don't see a black hole in your vision, do you? Your brain seamlessly fills in that missing information with a plausible background patch. You can try it with a simple demo. Mark a dot on a piece of paper, close one eye, and position the paper so the dot falls in your blind spot. The dot will disappear, and your brain paints in the empty area with the surrounding color or pattern. It's as if your brain runs a Photoshop autofill in real time, and you never notice a thing. Our vision is full of these constructive tricks. We have color-sensitive cones only in the center of our vision, not in the periphery. Yet the whole scene appears colorful to us because our brain fills in the edges with an assumed wash of color. We think we see a continuous, detailed world, but much of that detail is fabricated by the brain. Consider optical illusions. They exploit our brain's built-in processing rules. One classic example is Adelson's checker shadow illusion, a drawing of a checkerboard partly in shadow, where one dark square in the shadow and one light square outside the shadow are actually the exact same shade of gray. To our eyes, the shadowed square looks much lighter than the other because our brain is compensating for the dimmer lighting and perceives it as lighter. Your perception isn't faithfully reporting the raw data, which are identical grays. It's altering it based on context, usually useful, but in this case misleading. Or think of the viral dress image from 2015. Some people swore the dress was white and gold, while others saw blue and black. In that case, your brain was trying to subtract the color of the lighting. People who assumed the photo was lit by bluish daylight mentally filtered out blue and saw a white-gold dress. Those who assumed a warm, shadowy light filtered out yellow and ended up seeing blue-black. The image was ambiguous, so our brains made different guesses, with dramatically different results. Color, in fact, exists only in our perception. An object reflects certain wavelengths of light, but whether that looks red or blue or gold is determined by our visual system. As one cognitive scientist explained, neither objects nor lights are actually colored in anything like the way we experience them. Rather, color is a psychological property of our visual experiences, not a physical property of those objects or lights. In other words, your brain takes the raw light and creates color in your mind. Ever wonder if the red you see is the same red someone else sees? It's entirely possible people have slightly different subjective color experiences, and we'd never know because we can't get outside our own minds to compare. Vision might be our sharpest sense, but it's still highly fallible. And what about attention? We like to think if something important happens right in front of us, we'll notice. But the famous invisible gorilla experiment proves otherwise. Volunteers watched a video of people passing a basketball and were tasked with counting the passes, focusing intently on that. In the middle of the video, a person in a gorilla suit strolls through, even pausing to beat its chest. Afterward, when asked, about half the participants insisted they saw no gorilla at all. Their attention was so occupied that the obvious became invisible. This inattentional blindness can affect any of us. We routinely miss things in plain sight if we're not expecting them. If you've ever frantically searched for your glasses only to discover they were on your head all along, you've experienced a mild version of this. Our memory can be equally deceptive. We tend to think of memory like a video recording, but in truth, it's more like a story we reconstruct on the fly. Psychologists have demonstrated that memories can be distorted, or even implanted. In one study, people were told a convincing story of a childhood incident that never happened, and many of them later remembered it in detail, adding their own embellishments. Eyewitnesses to crimes often strongly recall things that conflict with camera footage or other evidence, because memory is reconstructive, not a perfect replay. Every time you recall an event, your brain may alter it slightly, integrating new info, filling gaps, smoothing inconsistencies. That's why two people's memories of the same event can differ wildly, and yet both be utterly certain. Your brain, with all its brilliance, is also a master storyteller. Sometimes it revises the past without telling you. So, what's the takeaway? Our senses give us a useful but extremely limited view of reality, and our brains actively interpret and misinterpret that input. We are surrounded by real phenomena we can't sense, and even what we do sense is heavily filtered and edited by the brain. In a very real sense, each of us lives in a kind of virtual reality constructed by our brain from sparse data, with plenty of creative license taken. It's humbling and a bit unsettling. You live inside a model of the world, not the world itself, and that model can be flawed. But rather than make us doubt everything, this knowledge should ignite curiosity. If our direct perception is so limited, what is out there beyond our senses? We've already started extending our reach with scientific instruments, revealing a vast world our ancestors never knew. We should also be cautious about trusting every thought and memory. Our internal reality simulator, the brain, is good but not infallible. We've established that our perception of reality is a kind of contrived illusion, effective for survival but not a full picture, and sometimes downright wrong. Now, let's move beyond the mind's interpretation of inputs and examine reality from a more physical perspective. What is the nature of the stuff out there that we're perceiving? You probably assume the objects around you are solid and substantial, that a chair is a solid chunk of matter. In our next section, we'll zoom in on matter itself and discover why solid things, including you and me, are mostly empty space. Get ready to learn that the solidity of the world is, in a sense, another illusion. Right now, you might be sitting on a chair or holding a phone. Both feel solid as solid can be. But prepare to have your mind blown. That solid matter is 99.99999% empty space. It's not a metaphor, it's literally true. If you could somehow remove all the empty space inside the atoms making up your body, compressing everything down, the entire human race, although 8 billion of us, would fit into the volume of a sugar cube. Yes, you read that right. All humans squished into a single sugar cube. How is this possible? Let's zoom in on an atom, the basic unit of matter. At the center of each atom sits a tiny nucleus made of protons and neutrons, and around it a cloud of electrons. The nucleus is incredibly small compared to the atom as a whole. Over a century ago, physicist Ernest Rutherford discovered this with a famous experiment. He shot tiny particles at a thin sheet of gold foil, and most went straight through as if the foil were mostly empty space, but a few bounced wildly backward. It was as shocking as firing a cannonball at tissue paper and having it ricochet. Rutherford realized the atoms in the gold must have a very small, dense core, which we now call the nucleus, that occasionally deflected the particles, while the rest of the atom is basically open space. Picture this. If an atom were the size of a huge baseball stadium, its nucleus would be only about the size of a peanut at the center of the field. The electrons would be buzzing around in the distant bleachers. Most of that stadium, and thus most of the atom, is just empty space. Indeed, the nucleus's diameter is about 100,000 times smaller than the atom's diameter. Given that, you might wonder, if atoms are mostly empty space, why can't we walk through walls or fall through our chairs? What stops us, if so much, of matter is nothingness. The answer lies in the powerful forces within and between atoms. Those electrons whizzing around may be tiny, but they move extremely fast and carry negative electric charge. When you bring atoms very close together, their electron clouds strongly repel each other, since negative charges repel negative charges. Think of a fast-spinning fan. When it's off, you can safely stick your hand between the blades. When it's on, the blades move so quickly they feel like a solid disc. Try to push your hand in, and it will get smacked away. Similarly, electrons, zipping around an atom, create a kind of force field that resists other electrons. The solid feeling is really the sensation of those electrostatic forces pushing back at you. Another way to say it, no two atoms ever actually touch. In the classical sense, when you sit on a chair, the atoms in your body aren't literally colliding with atoms of the chair. What you feel as contact is the electromagnetic repulsion between your electrons and the chair's electrons. It's like trying to push the same poles of two magnets together. They resist. In fact, on a microscopic level, you are hovering at any distance above the chair's surface. As a science writer quipped, you're not actually sitting on that chair. You're hovering ever so slightly above it. When you touch someone or something, the trillions of electrons in your fingers are repelling the electrons in the other object's surface. What you feel as solidity is the electrical resistance between atoms, not any physical substance pressing firmly together. And what about all that empty space between atomic nuclei and electrons? Quantum physics says that isn't truly empty. It's filled with fields, like the electromagnetic field, and possible fluctuations. Particles, like electrons, are really excitations, little ripples, in underlying quantum fields that extend through space. Even the vacuum of space is a seething baseline of these fields, sometimes producing transient virtual particles that pop in and out of existence. So, emptiness isn't so empty after all. It's more like a calm but active field. This is getting abstract, but the point is that solidity is a macroscopic illusion. Zoom in, and there's space and fields and forces, but very little substance we'd recognize. The nucleus itself, that ultra-dense peanut at an atom's core, is extremely solid in the sense of mass concentration. If you could hold a teaspoon of purely nuclear material, imagine compressing matter until electrons merge with protons, it would weigh billions of tons. In nature, this happens in neutron stars, remnants of supernovae where gravity crushes atoms so much that electrons and protons combine into neutrons and the whole star becomes essentially one giant nucleus. A chunk of neutron star matter the size of a sugar cube would outweigh Mount Everest. So yes, nuclei are incredibly dense. But luckily, in normal matter, these nuclei are spaced very far apart relative to their size. Remember, stadium versus peanut. The solid objects we interact with are mostly the space between nuclei stiffened by electromagnetic forces. Even the mass that gives objects weight is a bit strange on close inspection. Most of an atom's mass is in the nucleus, since protons and neutrons are 2,000 times heavier than electrons. But if we dig into those protons and neutrons, we find even they are mostly empty space and energy, composed of tiny quarks whizzing, inside bound by gluons. The crazy thing is, the mass of a proton doesn't mostly come from the quark's mass. It comes from the energy of their motion and the binding energy. Thank you, E each mc2. Essentially, matter is concentrated energy, and what we experience as mass is really energy stored in moving quarks and gluon fields. So even the solid nucleus is more like a bundle of intense energy than a little marble of substance. The take-home message is that the solidity of matter is a carefully orchestrated illusion. Atoms are 99.9999% empty space, yet to our senses, objects feel firm because of electric forces. If you could magically turn off the electric charges in atoms, you could walk through walls like a ghost. Of course, if you did that, you and the wall would both disintegrate into a plasma, so maybe don't try this at home. When two objects collide or you clap your hands, it's not truly solid surfaces hitting, it's the electromagnetic fields, repelling each other, and the particles never touch. Think about it. You have never actually touched anything in the way you might imagine. When you press your fingertip against a table, the electrons in your finger and those in the tabletop are pushing against each other. The table pushes back on your finger not because it's a dense slab of matter, but because at the atomic level, it's like trillions of tiny charged springs resisting compression. Matter is mostly void, held together by forces of nature, and that's why you don't fall through the floor. Next time someone calls you empty-headed, you can chuckle and say, "You're right, 99.999% empty, to be precise." In fact, everyone is mostly empty space, held together by whirling particles and fields. By now, your concept of a solid object should be forever changed. The ordinary solid world, the floor under you, the device in your hand, your own body, is built on an invisible scaffolding of electric forces and energy fields. It's not false to call things solid. They definitely feel solid, but it's profoundly true that under the hood, there's a whole lot of nothing there. We've seen that matter at a fundamental level is surprisingly insubstantial. Now, armed with that insight, let's tackle something we usually think of as even more absolute: time. We take it for granted that time marches forward uniformly for everyone. A second is a second, a minute is a minute. Right? Well, fasten your seatbelt, because in the next section, we'll discover that time itself can bend, slow down, or speed up depending on circumstances. Reality is about to get even stranger. Time, it's supposed to be the one constant in life, ticking steadily forward for everyone. But what if time can stretch and shrink? What if your 1 hour could be someone else's half an hour or 2 hours, depending on circumstances? It sounds like science fiction, but it's the startling truth of Einstein's theory of relativity. Moving fast or being in a strong gravitational field literally makes time run differently. Two clocks that start together will disagree if one is set in high-speed motion or taken to a place with different gravity. This isn't just conjecture, it's been measured and verified. Common sense tells us time flows uniformly, like a single giant clock in the sky that we all share. Einstein proved that idea wrong in the early 1900s. According to his special, Relativity, 1905, if you travel at a high speed, time slows down for you relative to someone who's not moving so fast. The effect is negligible at everyday speeds. Riding in a car or plane won't noticeably change your aging, but it grows dramatically as you approach the speed of light. Meanwhile, 10 years later, in his general relativity, Einstein showed that gravity also affects time. The stronger the gravitational pull you experience, for example, closer to a massive object or deeper in a gravity well, the slower your time runs compared to someone farther from that mass. In other words, time is not absolute. It's flexible and personal, woven together with space. This sounds like a plot twist from a sci-fi novel, but nature really works this way. In a famous illustration, imagine identical twins. One stays on Earth while the other boards a rocket ship. Suppose the rocket twin zooms away at 95% of light speed to a distant star, then turns around and comes back. The traveling twin might experience, say, 10 years of time during the round trip. But when she returns to Earth, she finds that far more than 10 years have passed for her stay-at-home twin, perhaps 20 or 30 years, depending on how fast she went and how long. The traveling twin is literally younger than her sibling. This is called the twin paradox. It's not truly a paradox. It's resolved by the fact that the traveling twin felt accelerations and changing speeds, which breaks the symmetry between them. It's been confirmed experimentally using precise clocks. In 1971, scientists flew atomic clocks on commercial airplanes around the world. When compared to synchronized clocks on the ground, the flying clocks had shifted in time by the exact amounts Einstein's equations predicted, on the order of a few hundred billionths of a second difference. The moving clocks ticked a bit slower. Special relativity's time dilation has also been observed in subatomic particles. For example, unstable particles called muons are created high in Earth's atmosphere by cosmic rays. Muons decay in about 2 millionths of a second on average. With that short a lifetime, even traveling near light speed, they shouldn't make it to the ground. But many do reach Earth's surface, because flying through the atmosphere at 99.9% of light speed, time runs slower for the muons from our perspective, extending their lives enough to complete the journey. Our GPS satellites are another everyday proof. These satellites whiz around Earth at just 14,000 km/h, fast enough to experience a bit of time dilation, and they orbit about 20,000 kilometers up, where Earth's gravity is weaker. According to relativity, a GPS satellite's clock should fall behind Earth clocks by about 7 microseconds, millionths of a second, per day, due to its high speed, special relativity, but also run ahead by about 45 microseconds per day, because gravity is weaker up there, general relativity. Net effect: the satellite clocks tick about 38 microseconds faster each day than identical clocks on Earth, and indeed, that's exactly what's observed. Engineers must correct for this difference. If they didn't, GPS positions would drift by kilometers each day. The fact that your phone's GPS can pinpoint your location within meters is a quiet validation that Einstein's wild theory is true. General relativity also gives us scenarios like the movie Interstellar, where one astronaut spends a few hours near a black hole and returns to find decades passed for those who stayed away. This is based on real physics. A very strong gravitational field, like that of a black hole, slows time dramatically. On that Miller's planet, near the black hole in Interstellar, 1 hour equaled 7 years back on the ship. An extreme example, but theoretically plausible. Closer to home, astronauts on the International Space Station age just a tiny bit slower than we do on Earth's surface, because of both their speed and being higher up in weaker gravity. In one famous example, astronaut Scott Kelly spent 340 days in orbit while his identical twin, Mark, stayed on Earth. When Scott returned, precise measurements showed he had aged milliseconds less than Mark. Not much. The ISS isn't fast enough or far enough out to produce a big effect, but the difference was real. Perhaps even stranger than time dilation is the fact that simultaneity is relative. Two events that appear simultaneous to you might not be simultaneous to someone moving at a different speed. For example, imagine you're on a moving train and you see 2 lightning bolts strike the ground at the same time, one outside the left window, one outside the right. An observer standing on the ground might see one bolt strike slightly before the other. This isn't because of a trick or signal delay, it's a fundamental feature of space-time. There is no single universal now that everyone agrees on. At high speeds or in different gravitational conditions, the order and timing of events can differ between observers. This shatters the notion that time is a single absolute flow. Instead, each observer has their own personal time, tied together with the space they occupy. If all this is scrambling your brain, you're not alone. These relativistic effects only become obvious under extreme conditions, like near light speeds or intense gravity, which is why we don't notice them in daily life. In our ordinary experience, a second is a second and simultaneous is simultaneous. But as far as nature is concerned, time and space are fluid. Einstein's equations have been confirmed by experiment after experiment, from minuscule particle decays to astronomical observations. We've even measured gravitational time dilation on small scales. In 2010, NIST scientists placed two ultra-precise clocks, with one just 12 inches, 30 centimeters higher than the other, and the lower clock, closer to Earth's center, ticked slightly, slower than the higher one due to the tiny difference in gravity. That's mind-bending. Simply being a foot higher made time run a bit faster. It's important to note that relativity doesn't let you do science fiction-y things like travel to the past or build a time machine that violates causality, while you can travel to the future by experiencing less time than others via high, speed or heavy gravity. You can't go back and change the past according to known physics. Still, the fact that we can bend our trajectory through time is astonishing. It means if you wanted to visit Earth's far future, you could in theory take a near light-speed rocket ride. For you, only a few years might pass, but you could return to find millennia have gone by on Earth. You'd have to leave everyone you know behind in the process, so it's a bittersweet kind of time travel. All this teaches us a humbling lesson. Time and space are not the fixed absolute backdrop we once assumed. They are part of the physical play and can be warped by motion and mass. In everyday life, we don't notice the warp, just like 2E. Someone walking on a vast curved Earth, the ground feels flat locally, but the curvature and warping are there, revealed in precise experiments and extreme environments. A second for me might not be exactly a second for you if we move differently or sit at different gravitational potentials. Reality's rules allow these counterintuitive outcomes, and they've been confirmed beyond doubt. Even our modern electronics and navigation rely on them. Without relativity, technologies like GPS and particle accelerators would not work properly. So the next time you're running late, you could jokingly blame it on time dilation. Sorry, boss, I was driving. So fast this morning that my clock ran slow. Though, unless you were orbiting a black hole, this excuse won't hold up. The deeper point is, time is not as straightforward as it seems, and we're not done with the universe's trickery. We've explored the strange but well-tested realm of relativity. Now, we're going to dive into something perhaps even more mind-boggling: the quantum world. If you think macroscopic effects like time warping are odd, just wait until you see what the fundamental building blocks of reality are, up to behind the scenes. Brace yourself for quantum mechanics, where reality gets downright spooky. Picture a cat in a box that is simultaneously dead and alive until you peek. It sounds like a twisted fairy tale, but this is actually a famous thought experiment in quantum physics, devised by Erwin Schrödinger, illustrating how bizarre the quantum world is. Down at the scale of atoms and subatomic particles, reality behaves in ways that defy logic. Particles can exist in multiple states at once, a phenomenon called superposition. Two particles can become entangled, meaning they share a unified state such that an action on one instantly influences the other, even if they're light years apart. And the simple act of observing or measuring a quantum system changes its state in a fundamental way. Welcome to quantum mechanics. Leave your common sense at the door. Let's break those ideas down, because they're as crazy as they sound. First, superposition. In the quantum realm, a particle like an electron doesn't have to be in one single place or state. It can literally be in a combination of states at the same time. It's as if you asked a quantum coin, heads or tails, and it answered both until you look. Only when you check, measure it, does it collapse into one definite outcome. Schrödinger's cat is a vivid, if morbid, illustration. A cat is sealed in a box with a quantum-based device that has a 50-50 chance to kill it after an hour. Quantum theory says after an hour, and before you look, the cat is in a superposition of alive plus dead, essentially both at once. It's only when you open the box and observe that the superposition collapses and you get a single reality, live cat or dead cat. Interestingly, some physicists propose that the cat doesn't really collapse to one state at all. Instead, both outcomes happen, each in a different branch of reality. This is the many worlds interpretation of quantum mechanics. Every quantum possibility spawns a new universe. In one branch, you opened the box to find a live cat. In another branch, a dead cat, and these worlds never interact. It's a mind-boggling idea, but it has a following among scientists who want to avoid the mysterious collapse concept entirely. If it's true, then reality is constantly splitting into countless parallel versions. Weirdly enough, that might mean in some universe the cat is alive and in another it's dead, and both are real. Schrödinger intended this scenario to highlight how absurd quantum rules can seem when applied to everyday objects. Yet something akin to this happens with particles constantly. This isn't just philosophical musing. Experiments demonstrate superposition plainly. Shoot a single electron through a barrier with two slits, and it behaves as if it went through both slits at once. On a screen behind the barrier, it creates an interference pattern, a series of light and dark bands, like a wave would, as if the electrons split into two waves that passed through both slits and then interfered with each other. But if you set up a detector to watch which slit the electron actually goes through, that very act of measurement forces the electron to pick one slit, and the interference pattern disappears. Now it acts like a particle going through a single path. Observation changes reality in the quantum realm. Importantly, it's not because a conscious mind is looking. Even an automated detector will do. It's the interaction of measuring. The detector inevitably disturbs the particle that alters the outcome. Nature doesn't allow you to know which path the electron took and still see the wave-like interference. Those behaviors are mutually exclusive. As one physicist wryly put it, the electron decides to act like a particle only if you watch it. If you're not watching, it's happy to act as a spread-out wave of possibilities. Next, entanglement, arguably even stranger. You can have two particles, say two photons of light, that are created together and become entangled. When particles are entangled, they share a single quantum state. They're like a perfectly coordinated pair. If you measure one, you instantly set the state of the other, no matter how far apart they are. It's as if you had two magic coins that are somehow linked, so that if you flip them, they will always land on opposite sides. Flip coin A here and get heads, and you instantly know coin B, even on the other side of the world, is tails. This correlation is immediate and doesn't fade with distance. Crucially, you can't use this to send a message faster than light, because you can't control the outcome of the measurement. But the fact of the correlation is real and beyond classical explanation. Albert Einstein, who found this deeply unsettling, famously sneered at it as spukhafte Fernwirkung, spooky action at a distance. He suspected there were unseen hidden variables that predetermined the outcomes so that the particles wouldn't truly be influencing each other instantaneously, which seemed to violate the cosmic speed limit of light. In 1964, physicist John Bell devised a theoretical test to check for such hidden variables, and starting in the 1980s, a series of ingenious experiments by Alan Aspect, John Clauser, Anton Zeilinger, and others carried out those tests. The verdict: nature really is spooky. The experiments, which earned Aspect, Clauser, and Zeilinger the 2022 Nobel Prize, showed that entangled particles have correlations that cannot be explained by any local hidden variables. In other words, the results violate Bell's inequality and align with quantum mechanics. Whatever is happening with entanglement, it's genuinely non-local. It's as if the two particles are two sides of one object, even when separated by kilometers or more. In 2017, Chinese scientists even demonstrated entanglement over 1,100 kilometers between Earth and a satellite, the Micius experiment. A photon on the ground became entangled with one on the satellite, and measurements showed the same. Spooky, instantaneous correlations. We don't fully understand how the universe does this. It doesn't appear to send any signal between the particles. It's like the universe just knows about their link, but it's now an experimental fact. Quantum mechanics thus forces us to accept a few wild truths. Reality is not deterministic on the microscale, it's probabilistic. Particles don't have definite properties or locations until they're measured. Until that interaction, they exist in a hazy state of possibilities. Einstein objected, God does not play dice with the universe, but experiments suggest that, at fundamental levels, randomness is woven into the fabric of reality. Also, objects that seem separate can be deeply connected, entangled, in ways that make a mockery of distance, though, thankfully, this weirdness mostly shows up only with very small things, not large objects, and certain properties can't be pinned down simultaneously. Heisenberg's uncertainty principle tells us you can't know a particle's exact position and exact momentum at the same time. The more precisely you know one, the more fuzzy the other gets. This isn't due to measurement flaws, but is a fundamental feature of nature. It's like reality keeps some secrets. You can know one aspect of a particle clearly only at the expense of knowledge about another aspect. There are other quantum phenomena too, like quantum tunneling, where a particle can vanish from one side of an energy barrier and appear on the other side without having enough energy to classically go over it. It's as if you tossed a ball at a wall and once in a while it just showed up on the other side of the wall. This is not just theory. Quantum tunneling is crucial to how the sun shines. It allows nuclear fusion to happen in the sun's core by letting particles get through energy barriers. And it's the principle behind technologies like the scanning, tunneling microscope, which can image individual atoms by exploiting electrons' ability to tunnel through tiny gaps. If macroscopic objects behaved like that, you might occasionally find yourself walking through a solid door purely by chance. Don't get your hopes up. The probabilities for big objects tunneling are effectively zero. If you find all this hard to imagine, you're in good company. Even the great Richard Feynman admitted, I think I can safely say, that nobody understands quantum mechanics. He didn't mean physicists don't use it successfully. The equations work exceedingly well. He meant that the actual behavior of quantum entities defies intuitive visualization. Our classical intuition simply isn't equipped for the quantum realm. We've had to train ourselves to accept the math and experiments even if the picture they paint is baffling. Our everyday logic just doesn't apply down there. Yet, weird as it is, quantum physics is profoundly real and practical. It underlies much of the technology we use. The semiconductors in your computer and phone's microchips only work because electrons obey quantum rules in materials, forming band gaps that let transistors switch on and off. Lasers operate on quantum principles, electrons dropping between energy levels. MRI machines in hospitals exploit quantum properties of atomic nuclei. Even the reason the sun produces energy fusion is, in part, quantum tunneling. And now we're developing new technology that explicitly uses quantum weirdness. Quantum computing aims to use superposition and entanglement to perform computations far beyond classical computers. And quantum cryptography uses entanglement and then a cloning theorem to enable unhackable communications. In 2017, scientists even used entanglement to teleport the quantum state of a photon from a ground station to a satellite in orbit, essentially transferring information via entangled partners. Don't worry, this can't beam up humans like in Star Trek. It only works for quantum states. The point is, we've taken this bizarre theory and built machines with it, and those machines work. Quantum mechanics, for all its strangeness, is the foundation of the digital and technological revolution around us. To sum up, quantum mechanics reveals a layer of reality where particles behave in ghostly, counterintuitive ways, a world where existence is smeared out until observed, where causality has a nearly non-local twist, and where probability rules. It's a realm that truly earns the label mind-bending. But as strange as it is, this is how the universe operates at a fundamental level. The familiar, solid, predictable world we experience emerges out of a substrate of uncertainty, entanglement, and wave-like fuzziness. After seeing all these ways in which reality defies common sense, it's natural to ask, what is reality then? We've peeled back multiple layers. Our senses give us a partial, sometimes misleading, view. Matter is mostly empty space. Time and space are flexible. And at the deepest level, existence is fuzzy and probabilistic. Some thinkers have taken these insights to an extreme conclusion. Perhaps reality as we know it is not ultimate at all. Perhaps we're inside some higher level construction, like a cosmic simulation. It's a wild idea, But given how much of what we've discussed already feels like a grand illusion, it's a question worth exploring. In our final section, we'll delve into the simulation hypothesis, the suggestion that our universe might be an elaborate program run by an advanced intelligence, and consider why some scientists and philosophers take this seriously. Prepare for one more leap down the rabbit hole. We've journeyed through layers of reality's weirdness, but now we arrive at a truly mind-bending question. What if everything we've ever known, the Earth, the stars, your entire life, is actually just data inside some cosmic computer program? In other words, are we living in a simulation? This idea, which sounds straight out of the Matrix, has been seriously considered by some philosophers and scientists. It suggests that our reality might be an extremely advanced virtual reality, created by some intelligence, perhaps future humans or an alien civilization. It's a speculative hypothesis, but some arguments say it's not only possible, but perhaps statistically likely. The modern formulation of this argument was given by philosopher Nick Bostrom in 2003. He essentially proposed a trilemma. 3 possibilities, at least one of which must be true. No civilization ever reaches the technological capability to run ancestor simulations. In other words, all civilizations go extinct or destroy themselves before developing the ability to simulate conscious beings. Advanced civilizations do have the technology, but choose not to run a significant number of simulations of their evolutionary history. Maybe they have strict ethics against it, or just no interest. Advanced civilizations do run many simulations of worlds with conscious beings, and, therefore, the number of simulated beings would vastly outnumber the beings in the one real, base universe. If that's the case, then statistically, we are almost certainly living in a simulation, because it's far more likely we're one of the countless simulated minds rather than one of the rare original biological minds. In Bostrom's view, if you reject the simulation hypothesis, you have to conclude that either no civilization ever gets to that advanced stage, or that every advanced civilization opts out of making simulations. But if it's at all common to create such simulations, then the sheer number of simulated realities would overwhelm the single original reality, making it a near certainty that we're in a simulation. It's a probabilistic argument, not proof, but it's logically compelling given its assumptions. This argument captured a lot of attention. Even famed tech entrepreneur Elon Musk has said he finds it compelling, quipping that the odds that we're not in a simulation are 1 in billions. He reasons that if humans eventually can create indistinguishable virtual worlds, then it's unlikely we just happen to live in the single real world instead of one of the many simulated ones. Others, like astrophysicist Neil deGrasse Tyson, have put the odds at maybe 50-50, acknowledging it's a plausible hypothesis. These proponents often point to how rapidly our own technology has advanced. In just a few decades, we went from crude computer games to hyper-realistic 3D simulations and VR. Project that forward thousands or millions of years, and the capability to simulate entire universes with conscious inhabitants doesn't seem outlandish. However, before you start wondering which of your friends might be NPCs, non-player characters, in the game, let's emphasize, this is still hypothetical. Unlike the phenomena we discussed earlier, we have no direct experimental evidence of a simulation. It's a philosophical and statistical argument at this stage. So, what evidence could we look for? Some scientists have mused about finding glitches in the matrix. For instance, space and time might have an underlying grid or resolution limit if it's a simulation. So maybe at extremely high energies or large scales we'd see deviations in physical behavior, akin to noticing the pixels in a digital image when you zoom in too far. One proposal suggested that if the universe is simulated on a lattice, grid, there might be a slight directional dependence in the behavior of ultra-high energy cosmic rays reflecting the lattice's orientation. Researchers have examined cosmic ray data for such symmetry-breaking clues, but so far, nothing conclusive has been found. Another idea, perhaps a simulation, might have to approximate complex physics, which could show up as tiny anomalies in experiments, like rounding errors, in the values of physical constants, or slight violations of conservation laws under certain conditions. To date, physics experiments have not revealed any glaring digital fingerprints, The laws seem smooth and continuous as far as we can tell. Philosophically, there are many debates about the simulation hypothesis. One issue concerns consciousness. Bostrom's argument assumes that simulated minds in a computer could be conscious, what philosophers call substrate-independent consciousness. If that's true, if a sufficiently detailed simulation of a brain would have genuine subjective experiences, then simulations could contain beings like us who feel alive. But not everyone agrees this is possible. Some argue consciousness might require some special quality of biological brains or quantum processes that a computer program can't capture. We simply don't know enough about consciousness to be sure. It's an open question whether a simulated person would truly be aware or just act aware, and how would you even tell? Another issue is testability. If we are in a perfectly designed simulation, can we ever prove it from inside? If the simulators don't want us to find out, they could conceivably adjust the simulation to remove any evidence we discover, like fixing a glitch in a video game via a patch. It's possible the simulation hypothesis is not falsifiable. Anytime we think we found proof, that proof itself could be part of the simulation's design or could be erased by an update. This makes some scientists dismiss the idea as not scientifically useful. It might be impossible to ever get a definitive answer if the simulators are clever. It falls more into metaphysics than physics in that sense. There's also a practical argument. Maybe the amount of computing power needed to simulate an entire universe down to every atom or quantum event is so immense that even a super-advanced civilization can't muster it. Advocates counter-argue that a simulation could be optimized. It might not simulate every atom all the time, only when needed, like how video games only render what the player is looking. Interestingly, quantum mechanics' odd observer effect, where things aren't determined until observed, kind of mirrors that idea. Some have whimsically suggested that the reason quantum particles don't have definite states until measured is because the simulation is saving on computation by not rendering properties until someone checks. This is more tongue-in-cheek than serious science, but it shows how these ideas can spark creative thinking. Critics also ask, if we are simulated, why would our creators simulate us? Perhaps it's for research, ancestor simulations, to see how their own evolutionary history played out, or for entertainment. Maybe our simulator is an uber-advanced teenager running Universe Tycoon on their computer, or for some art or educational project. Those are wild speculations, of course. There's also the simulation nesting problem. If our reality is simulated, what about the reality that contains our simulators? Could they too be simulated by an even higher reality? This could lead to an infinite regress of simulations within simulations, though Bostrom pointed out that at least one level has to be base reality, or the chain couldn't start. Either way, it's turtles or simulations, all the way down until you hit the bottom layer of actual reality. Now, let's say, purely for the sake of argument, that we are in a simulation. Would it change anything about how we should live, or how we feel? This is more of a philosophical question. In The Matrix, Neo is horrified to discover his world was an illusion and humanity was enslaved. But our scenario is different. If our world is a simulation, it's not necessarily dystopian or controlled by evil overlords. It might be a totally natural feeling virtual world. Your experiences would still matter to you. If you stub your toe, it hurts. Simulated nerves are not. If you fall in love, the emotions are real. Our meaning and values wouldn't suddenly evaporate, just because the substrate of our reality is code. As Descartes argued with his evil demon thought experiment, which was basically the 17th century version of we live in a fake reality, even if everything around you were a deception, your own conscious experiences undeniably exist. I think, therefore I am. Simulated or not, you are. In a practical sense, we'd still have to play by the rules of the universe we're in. Physics would be the program rules, and thus far, they're consistent and inviolate, so we have to respect them. Perhaps the only difference is if we knew we were in a simulation, we might try to reach out beyond it. Hey, programmers, can you fix climate change for us? But unless the simulators reveal themselves, we have only one reality to interact with. This one. It's our home, whether it's real or virtual. The simulation hypothesis is essentially a high-tech reboot of old philosophical questions. Plato's allegory of the cave, circa 400 BCE, analogized humans to prisoners chained in a cave, seeing only shadows on a wall cast by things passing in front of a fire behind them. They take the shadows as reality because it's all they've ever known. But then one prisoner is freed and sees the outside world, a vastly greater reality, and realizes the shadows were an illusion. Likewise, many religious and philosophical traditions have considered the world we perceive to be a lesser or illusory reality compared to some higher plane. Consider the concept of Maya in Hindu philosophy, the illusory nature of the world, or Gnostic ideas of our world being a flawed creation by a lesser deity. René Descartes, 1641, imagined a malicious demon deceiving him with an illusory external world, and he struggled to identify what he could know for certain, landing on his own existence as a thinking entity. Fast forward to 1999 and The Matrix. Film popularized the idea in pop culture, humans living in a simulated reality generated by AI. The simulation argument is basically this ancient, how do we know what's real? Question dressed in cutting-edge scientific attire. It doesn't prove we're in a simulation, it just gives a scenario under which being in a simulation would actually be more likely than not. So, are we living in the Matrix? We have no evidence of it, and it remains just an intriguing possibility. Some very smart people take it seriously as a hypothesis. Others roll their eyes at it. It's one of those ideas that currently sits more in the realm of philosophy or even science fiction thought experiment than testable science. As of now, it's more likely we live in a genuinely physical universe that just so happens to be unbelievably weird, as we've been discovering. But the simulation idea can be a fun mental exercise. It forces us to examine why we believe what we believe about reality and how we would, or wouldn't, know if we were deceived on a cosmic scale. At the end of the day, whether or not our reality really real, it's the only reality we've got. If anything, the simulation hypothesis reminds us not to take things at face value and to always be open to profound surprises about existence. And on the off chance it's true, maybe our cosmic programmers are enjoying watching us unravel the rules of the reality they set up. We set out with the goal of shaking the foundations of how you see the world. By now, you've witnessed a parade of mind-bending truths. Your senses, reliable as they feel, only show you a tiny slice of reality. And even within that slice, your brain is filling gaps and sometimes outright deceiving you. Thessalid, stable matter you interact with is, on an atomic level, almost entirely empty space, held together by energetic forces. Time and space, which in our daily lives seem absolute, turn out to be flexible, warped by speed and gravity. And the quantum realm underlying everything behaves in ways so bizarre that even the brightest minds struggle to wrap their heads around it. Particles existing in multiple states at once, influencing each other from across the universe, and refusing to take on definite properties until observed. We've even entertained the possibility that everything we perceive might be an elaborate illusion, a simulation, created by entities beyond our reality. It's been a wild ride. What do we do with this knowledge? For one, it can instill a sense of humility. We humans have a tendency to assume we know how the world works, but history shows that every time we thought we had it all figured out, reality threw us a curveball. We thought Earth was the center of the universe. It's not. We thought time and space were absolute. They aren't. We thought atoms were solid balls. They're mostly empty. We assumed the act of observing doesn't affect things. In quantum mechanics, it does. It seems the more we learn, the more we realize how much we don't know. Embracing that humility is a good thing. It keeps us curious and ready to learn more rather than complacent in a comfortable delusion. This knowledge should also spark a sense of wonder. The world is far more fascinating and intricate than it appears in our everyday experience. When you realize that you're only seeing a small sliver of the electromagnetic spectrum, doesn't it make a sunset or a rainbow even more poignant, knowing there are countless colors your eyes will never see, but are nonetheless there? When you understand that you're hovering above your chair thanks to electron forces, Doesn't it make you marvel at the invisible dance of physics happening beneath you? The fact that time can dilate and future astronauts could leap forward in time, doesn't that transform the way you think of a simple ticking clock? And the notion that there's a whole quantum world of particles zipping and entangling and tunneling inside the solid surface of your table, that turns the mundane into the magical. As the physicist Richard Feynman, whole of the beauty of nature's mysteries, said, I have approximate answers and possible beliefs and different degrees of certainty about different things, but I'm not absolutely sure of anything. That attitude of awe and open-mindedness is exactly what these revelations encourage. It's worth noting that learning about these mind-bending aspects of reality isn't just an exercise in blowing your mind, though it certainly does that. It has practical benefits. Without understanding atomic and quantum physics, we wouldn't have electronics, lasers, modern chemistry, or medical imaging. Without understanding relativity, our GPS satellites would miss sync, and our particle accelerators would malfunction. Every fundamental insight we gain tends to unlock new technologies and capabilities. So, grappling with the true nature of reality also empowers us to shape our world in new ways. Perhaps most importantly, recognizing that reality is not what it seems can make us comfortable with the unknown. Instead of fearing the fact that there's so much we don't see or comprehend, we can find it exhilarating. It means there will always be more to discover. Our voyage of discovery is far from over. There are deep oceans left to explore, distant planets to visit, subatomic particles to understand, maybe even parallel universes or higher dimensions to probe. Not knowing everything isn't a sign of failure. It's the driving force for progress. So, as we conclude this epic exploration, take a moment to appreciate the mystery and majesty of the universe. We started by examining the very reality in front of your nose and found surprises lurking in the light that reaches your eyes and the solidity beneath your fingers. We went out to the cosmic scale of time and space and found they're not the straightforward stage we assumed. We dove into the microscopic and found it operates by rules that sound like fantasy. What we've learned is that the universe is full of surprises, and that's a wonderful thing. It means there will always be new horizons to seek, new questions to ask, new magic behind the curtain to reveal. My advice: stay curious, stay amazed, and enjoy the quest for understanding. The real reality, however strange and complex, is out there waiting for us to keep exploring. After all, part of being human is our drive to push beyond the limits of our senses and intuitions, to continuously update our mental picture of the world. Each time we do, the world becomes a little more incredible. As biologist J.B.S. Haldane famously said, the universe is not only queerer than we suppose, but queerer than we can suppose. Sources for the scientific claims and quotes in this text are listed below, so you can explore further and verify these facts yourself. Yules. Of the reality they set up,